Welcome back to the Deep Dive. Today we are strapping in for what might be one of the most fundamental questions in computer science, and frankly, in the philosophy of mathematics.
It really is.
How do we build a truly universal computer? And maybe more importantly, how do we prove what it can actually solve?
It's the foundational question. Before we can talk about efficiency, whether an algorithm is fast or slow, whether it takes, ON or ON squared time, we first have to settle the massive existential question of computability.
Exactly. Can a problem be solved at all? Our mission today is to move from the vague, intuitive idea of calculation, the way we learn to do long division in school, to a definition of mathematics that is so precise, so rigorous, that a machine can understand it.
And this journey is all about the power of abstraction.
Abstraction.
Yeah, and that abstraction is the secret sauce of computer science. It's how we take a messy, ambiguous, real-world scenario full of noise and physical constraints and boil it down into a pure, clean, mathematical object that a machine can manipulate.
Okay, let's unpack this. Before we can write any code for a machine, we have to translate the physical world into something a machine understands. Let's take a classic example. Weather forecasting.
Right.
It feels incredibly complex. We have a real-world problem. Given temperature, atmospheric pressure, wind speed, cloud cover. How long will it rain tomorrow?
That is a very human way of describing it. You have inputs and you want an output. But for computer scientists, we have to abstract away rain and wind as these sort of poetic physical concepts.
So what do?
We simplify the problem by defining it as a function. Let's call it $5.
That function, $5, maps the input data, our weather measurements, all those numbers representing temperature and pressure onto a solution.
Which is the answer, yeah. Maybe a duration in hours, also represented by a number.
And this mapping is the key. The formal condition for solvability states that a problem is solvable if, and only if, the function that describes it is computable.
But we immediately run into a problem, or rather the first necessary abstraction. What's the fundamental nature of that input and output? What are we working with?
In the purest sense, computer scientists and mathematicians have settled on the most elegant starting point. It's actually sufficient to consider functions that map tuples of natural numbers, so positive whole numbers, including 0 to a single natural number.
We write this formally as yoete to nethera. A sequence of Tycho numbers goes in, and one number comes out.
Now, this is where you, the listener, might immediately raise an objection. Why numbers?
Yeah, that's the obvious question. My laptop spends 90% of its time dealing with text, images, video, code itself. I don't just add numbers all day.
That's a great challenge. We work constantly with strings of characters, what we call word functions. These are functions mapping words over some alphabet. Let's call it sigodal, in other words, sigmadal.
And that little asterisk just means any sequence, any length of characters from that alphabet.
So for our mathematical proofs to hold true, we need to guarantee that the class of functions dealing only with natural numbers is exactly the same power as the class of functions dealing with text.
If those two concepts are equivalent, our mathematical proofs become universal. They apply to arithmetic and to every email you send.
Which brings us to the flaw in relying on just human intuition. We all have this informal idea of what computable means.
Sure.
If I ask you, can you compute the sum of these two numbers? You intuitively say yes. The informal definition is something like, a function is computable if there is a finite, unambiguous description of an effective procedure, an algorithm that uses only elementary local steps.
And that concept, effective procedure, is the heart of human calculation. But for formal theory, it is the poison of imprecision.
The poison of imprecision. I like that.
We need rigorous, universal statements. If we rely on vague, intuitive definitions, we risk chaos.
Imagine the nightmare scenario. We could end up defining computation based on the tool we use. We can argue that a function is, say, Java computable, but somehow not Python computable just because one language has a built-in feature the other doesn't.
Or worse, we might have definitions dependent on hardware. This calculation is only supercomputer computable. Or maybe something is biochemically computable, but not silicon computable.
We can't have that.
Yeah.
We need a definition that transcends the silicon, the programming language, and the person holding the pencil.
Yeah.
We need statements that are universal, independent of the specific mechanism doing the calculating.
So to create a mathematically useful definition of computation, one we can actually prove theorems about, it had to meet 3 strict requirements.
Okay, what's requirement 1?
It must achieve complete abstraction. It has to abstract away from concrete hardware and software. The physical implementation, whether we use silicon chips, gears, or a pencil and paper, must be completely irrelevant.
Requirement 2.
It must be general enough to encompass all those intuitive notions of computation we just talked about. It has to be universal. If a human can reliably follow a set of steps to get an answer, our formal model must be able to do it too.
And requirement 3.
It has to be mathematically precise and manageable for proofs. If the model is too complex, we can never prove its limits. We need something simple enough that we can actually use foundational logic and induction to prove its capabilities.
This challenge seemed, well, insurmountable in the early 20th century. But the pursuit of this definition led to the greatest conceptual milestone in the history of computation.
And that milestone tied all these requirements together. The Church-Turing thesis.
So we've established this massive requirement, finding a single, formal, universal definition of computation that anchors everything. And that's exactly what the Church-Turing thesis provides.
It truly is the universal bridge. It connects the purely abstract, formal world of mathematics, things like logic and set theory, to the messy, practical world of calculation and algorithms. The intellectual leap that Alan Turing and Alonzo Church made here fundamentally changed science.
So what exactly does the thesis claim?
It asserts that three specific classes of functions are entirely equivalent in their computational power. They're exactly the same size.
Okay, so what's the first class?
Class 1. Functions that are mini-pi computable. This is the formal, minimal programming language model we're going to dive into, designed specifically for rigorous proof.
Class 2.
Functions that are Turing computable. These are defined by the abstract machine model, the Turing machine, which conceptually is the simplest possible computer. It has an infinite tape, a head that reads and writes one symbol at a time, and a finite set of internal states. It's absurdly simple, but completely universal.
And the third class. This is the one that connects to us.
And class 3. Functions that are intuitively computable. This includes any effective procedure that can be carried out step by step with pencil and paper by a human without needing judgment or intuition or creativity.
Just a set of mechanical instructions.
Exactly.
And the thesis claims these three classes are exactly the same size. Everything that can be intuitively calculated can be calculated by a mini-pi program, and everything a mini-pi program can do, a Turing machine can do.
And the evidence supporting this is overwhelmingly empirical. What's fascinating here is the power of simulation. Since the 1930s, scientists have devised countless other models, lambda calculus, register machines, even DNA computing models.
And every single one of them.
Every single one of them has been shown to be able to be simulated by and in turn simulate the standard Turing machine.
You mentioned future paradigms, too. That's an important point for you, the listener. Even when we talk about quantum computers, which are incredibly fast for certain problems. The current understanding, which is sometimes called the strong Church-Turing thesis, is that a quantum computer can still be simulated by a standard Turing machine.
Albeit much, much slower. The quantum computer doesn't solve any new class of problems, it just solves certain computable problems a lot faster.
Which means the Turing machine, and by extension mini-pi, sets the absolute boundary of what is computable in the known universe.
Precisely.
Now let's clarify something that is absolutely critical. Why do we call it a thesis and not a theorem?
That is a fundamental distinction. A theorem is a statement we can prove using mathematical logic, given a set of axioms. The CT thesis is not a mathematical theorem.
You can't prove it.
Well, we can prove that mini-pi and the Turing machine are equivalent models. That's a theorem. But the leap linking those formal models to the vague concept of intuitively computable, that's a philosophical assertion. It's a hypothesis about reality.
So it's a hypothesis accepted, not because it's been logically proven from first principles, but because every attempt to define computation formally has failed to find a model more powerful than a Turing machine.
It's the strongest empirical evidence imaginable in a theoretical field.
The massive implication of accepting this thesis is that we simplify everything from this point forward. We get that universality we were looking for.
Exactly. We no longer need to distinguish between Turing computable or Python computable or Excel macro computable. We just use the universal term computable.
And we formally designate the class of all such functions as FOUR.
Which has tremendous practical application. For you, the programmer or mathematician, this simplification is liberation. If you want to prove that a function is computable, you only need to show any algorithm for it. In Python, pseudocode, whatever. The thesis guarantees it falls into the classes.
But the converse is even more powerful. To prove something is not computable, that no algorithm in any language on any hardware can ever solve it, you just have to show that it fails on the most restrictive, simplest model.
Like a Turing machine or MiniPy. It acts as the minimum standard. If a problem breaks the simplest machine, it breaks every machine. That simplification is why the Church-Turing thesis is so foundational.
We now have our universal benchmark. But to make these universal statements and formal proofs, we can't use massive, messy languages like Python or Java.
No, absolutely not. They have thousands of commands, layers of abstraction. It's just too complex to prove anything about them from the ground up.
If we had to prove that every feature in Python, its scoping rules, its garbage collection, was necessary for universality, we'd still be arguing about it.
The goal is to strip the language down to the absolute mathematical minimum, the structural essence of computation.
And this is the driving force behind our minimal model of computation, MiniPy. It's designed to be mathematically rigorous, simple enough for proofs, but powerful enough to simulate every modern high-level language.
Let's look at how it's built. It has to have the power of a Turing machine, but in a familiar programming style.
First, the variables are simple, sequences of letters and numbers, like by one or count. But the way we manipulate them is, well, it's brutal in its simplicity.
There are only two basic change operations.
Those two.
Only two, which are the atomic units of calculation. We have increment, variable plus min 1, and decrement, variable medius 1. That's it. No assignment, no direct addition, no multiplication.
And for control flow, the structures that guide the execution. We need sequence, obviously, doing one thing after another. But what's the key?
The single most crucial structure that provides the power is the loop, specifically the while loop, while variable equals 0p.
So this conditional loop, which repeats a set of commands until a variable hits 0, that's the core source of power.
That's everything. Anything complex, conditionals, for loops, even basic addition, must be synthesized from just these three elements: increment, decrement, and the while loop.
This looks readable, but the mathematical rigor lies in the semantics, what the memory state is, and how these simple commands actually change that state.
Right. We define the state of the program, the memory map, as a function that maps variables only to natural numbers. So we're only ever dealing with non-negative integers, 0, 1, 2, 3, and so on.
And this is where a really important mathematical constraint comes in.
Right.
What happens if we try to subtract from 0? This is the modified subtraction rule.
Yes. If the value of a variable $6 is, say, 5, and we decrement it, we get 4. That's standard. However, if the value is already 0, the result remains 0.
The system just clamps at 0. You cannot go negative.
Precisely. We can't allow negative numbers in the MiniPy memory space because the entire foundation of the model is built on the properties of natural numbers. It keeps the model pure and minimal.
So we have this Spartan language. Can it even perform basic arithmetic? Let's prove that addition works.
This is the first demonstration that minimalism doesn't equal weakness. The program for addition, 1fxy equals x plus y, is actually quite elegant.
What is it?
It's while y, 0.x plus 1, y equals 1, 1.
The logic is clear enough to a human. We repeatedly add 1 to $6 while simultaneously subtracting 1 from Yang until Yang's exhausted. When he reaches 0, $6 holds the original sum. But we need a formal proof.
We prove this formally using induction over dollars, the input value of Yang's.
Okay, the base case.
If 1 Yang's, the condition y, fails immediately. The loop is skipped, and $6 remains non. The result is 1 plus dollars, which is $1 it holds.
Now for the inductive step. Let's assume the program correctly calculates addition for some value, say 1 $. We have to prove it works for 1 gauze plus dollar.
Right. So if yk plus $1, which is not 0, the loop executes exactly once. In that first iteration, $6 increments to 1 plus dollars and all decrements to dollars.
And now we have a new state. $6 is dollars plus a long, and Yang is $1.
Because of our induction hypothesis, we are guaranteed that the rest of the loop, which is designed to add the value of Yang to the value of 6, will correctly calculate 1 plus 1 plus k.
And of course, 1 plus 1 plus k simplifies to $1 plus k plus $1. The induction holds true. This extremely simple loop proves that addition is MiniPy computable.
And by building addition, we unlock vast computational power. We can then prove that MiniPy can compute all the elementary mathematical functions you need.
Addition, modified subtraction, multiplication,
Which is just repeated addition.
integer division, and modulo.
All of which will be essential later when we start dealing with text. We won't use string functions, we'll use these numerical tools to decode data.
Now, in practice, If we're writing a complex program, we don't want to rewrite the addition loop every time, so we use shorthand or macros.
A macro in this context is just a pure text substitution. We can write add xy as a shorthand for that 3-line while loop. It's just for readability.
But here we hit a danger that highlights the rawness of this minimal model.
Yes, because MiniPy is defined to have only one global variable space and no local scope for functions, we run a serious risk.
Wait, why can't it just have local variables like Python does?
Because that's the catch of minimalism. To implement local scope, the language needs a whole complex memory management system. A stack to push and pop variable states, pointers, all of it. That would destroy the mathematical simplicity we need for proofs.
So because we lack that complexity, we get the danger of variable capture.
Exactly. If I write a macro add that needs a temporary helper variable inside it, let's call it temp, and then I use that macro in a main program that also happens to use a variable named temp.
The macro will unintentionally manipulate or trash the main program's temp.
It will, an unwanted side effect. In formal MiniPy, we have to guarantee safety by defining our macros to only use unique, globally reserved variable names. It shows that simplicity in the model often forces complexity in how you use it.
We've established that MiniPy is mathematically defined, pure, and capable of basic arithmetic. The crucial next step is to prove universality, that MiniPy is equivalent to a real-world language like Python.
This is the equivalence proof. We have two directions. Direction 1 is easy. MiniPy is no more powerful than Python.
Right, we can just take any MiniPy program and write a thin wrapper around it in Python. Python already handles integers.
The only slight adjustment we need is simulating that modified subtraction rule.
Yep.
Instead of x max 1, we just write something like x max 0 by 1. Trivial.
Direction 2, however, is the real deep dive. Python to MiniPy. We have to show that every complex feature Python offers can be built using only increment, decrement, and the while loop.
Let's start with variable assignment and control flow. Constant assignment, like Excel's 5, is done by first zeroing $6 and then incrementing it 5 times. Simple, but slow.
But the variable copy x least y is where we hit our first real obstacle, thanks to that modified subtraction rule.
Exactly. If we just try to write a loop that decrements dollars and increments $6, we successfully copy the value, but we also destroy the original value of Vader. It's a destructive read.
And we need non-destructive reading. So how do we do it?
We have to use helper variables. If our goal is x equals y without harming dollars, we need 2 auxiliary variables, say a prime and x prime.
Okay, walk me through it.
We use a loop that runs while the original y is not 0. Inside this loop, we do 3 things. Decrement y, increment our target x, and increment our helper I prime.
Let's track that. Say y starts at 10, the loop runs 10 times. So y goes to 0, x goes to 10, and I prime also goes to 10.
Correct. When that first loop finishes, the job is half done. X now holds 10, the correct copied value, but y is 0. The helper I prime holds the original value.
So now we use a second loop to restore y.
A second loop, we run while I prime equals 0, and inside we decrement I prime and increment y. This restores y from 0 back to 10.
That is an insane amount of work. 2 whole loops and 2 extra variables just to copy one number. It makes you realize how much Python is doing behind the scenes with a simple equal sign.
It's incredible. Now what about branching logic, like if statements? Python has if x equals 0, 0. P2MiniPy only has while.
So we have to simulate the if using a while loop that's guaranteed to run at most once?
Exactly. The key is setting up a control flag. Let's say we want to execute a command block $, only if $6 is 0.
How do we set that up?
We first check $6. If $6 is 0, we set an auxiliary control variable, let's call it $2 to oneers. If $6 not 0, we set $76.
Then we execute the main conditional block while C, 0, PC equals 1.
And that does it. If $6 is 0, $6 in dollars. The loop runs once, executes $, and immediately sets CDOs to 0, preventing repetition. If its $6 was not 0, is accent and the loop is skipped entirely. We've successfully simulated an if statement.
This recursive build-up addition from increment-decrement, if statements from while loops, is the proof that complex code is merely an elaboration of simple numerical steps.
And that leads us to the biggest intellectual hurdle for you, the listener, the data problem. Since MiniPy only works on numbers, how do we handle text or images or even the code itself? This is where we confirm the profound analogy that everything is a number.
This is the core of abstraction in modern computing. Every piece of information has to be encoded into a single massive natural number before MiniPy can process it.
This is sometimes called Gödel numbering. Let's look at text. Say we have an alphabet sigma with no characters. If we use standard ASCII, 100 and 200 until we odds, we assign a unique numerical code to each character from 0 to 127.
Okay, so every character is a number. Then what?
We then choose a base, battlers, that is larger than other. So let's choose $129. Using a bigger base guarantees our number system has enough unique digits to represent every character code.
And any word or string is then treated as a single enormous number written in that base, $129. The character codes themselves become the digits of this giant number. This is the biotic representation.
Right. In base 10, the number 423 means $4, and then 12 plus 2 $101 plus 3 $100. Now imagine the string cracked type. We find the numerical code for C, A, and T. Let's say there's 67, 65, and 84.
So the whole string CRTAT is encoded as one giant number.
Code C times 129 squared plus code A times 129 to the first power plus code times 129 to the 0 power. Every distinct string corresponds to one unique, massive natural number.
And the size of this number must get astronomical very quickly. A 5-page document would be a number with thousands of digits in base 129.
Precisely. But mathematically, it's still just a single natural number. And since MiniPy can work on any natural number, we assume infinite memory in the model, it can manipulate this entire document.
Once we have this giant number, we need to manipulate it using MiniPy's simple arithmetic tools. We throw away high-level string functions like findLength or getchar.
We use math instead. Consider finding the length of the string. The length is just the number of digits in that base 129 representation.
And how do we find the number of digits using only our basic arithmetic?
We use integer division. Think about base 10. To find the digits in 423, you divide by 10 to get 42, divide by 10 to get 4, divide by 10 to get 0. You count in 3 steps.
We do the exact same thing with our coded number. We repeatedly perform integer division by the base, 129, until the number is 0, and we just count the steps.
This is a beautiful example of abstraction. We're not processing text, we're performing arithmetic on a massive number, and the resulting count just happens to correspond to the number of characters.
What about accessing a specific character? If I want the third character in sec, which is T, how do I isolate its code, 84, from that giant number?
This requires 2 stages of mathematical isolation, integer division and modulo. Remember, the characters are stored as digits, and their position is determined by the power of the base.
T is the last character, so it's at the $1,290 position.
If we want the 8th character from the right, at position $, we first need to shift that character's code to the ones place. We do that by repeatedly dividing the coded number by the base, batal times.
So if I want the digit associated with $12,922 to be in the ones place, I divide the whole number by $12,992.
Correct. Once we do that shift with integer division, the desired character code is sitting in the ones place. Everything to the left is just noise we need to discard.
And to discard that noise, we use the modulo operation.
Yes. We take the result of that shifted number and calculate modulo 129. The modulo gives you the remainder of a division. Since the number in the ones place is a digit between 0 and 128, the remainder will be exactly that digit, the code of the character we wanted.
It is genuinely mind-blowing that this simple arithmetic, built entirely from increment and decrement, is all that is needed to simulate complex string processing.
And what about encoding complex data types beyond text, like negative integers, floating point numbers, lists, objects?
If a computer can process text and text can be encoded as a number, we have a way forward.
The simulation is recursive. We just reduce everything else to strings first. We can represent any complex structure as an ASCII string.
A negative number. We just write it as the string minus 42.359. That string is then encoded as a massive number, and MiniPy can parse that string using the arithmetic tools we just built.
Lists are handled the same way. We define them recursively. A list is a pair of value rest of list. We can represent that as a string like 42, 10, none, which we can then encode as one enormous natural number. All complex objects ultimately reduce back to string encoding, which is finally a number.
And the final piece of the universality puzzle, recursion. In high-level languages, we define functions in terms of themselves. MiniPy only has the while loop. Does that mean it can't handle recursive problems?
That's another powerful proof. Any function that is computable via recursion is also computable exclusively using iteration, using while loops. The power of computation is entirely captured by the ability to loop until a condition is met.
So, by showing MiniPy can simulate all the core features of Python assignments, control flow, and all data types via numerical encoding, we prove that MiniPy, despite its mathematical minimalism, is a universal programming language.
And we confirm the power of the Church-Turing thesis.
So what does this all mean for us? We've covered a tremendous amount of ground, moving from a vague idea of calculation to a formal model that guarantees universality.
We need to pull out the two major conclusions for you, the listener. The first is about capability and abstraction. The simple, minimal, mini-pi language built from only increment, decrement, and the while loop is universally capable.
If a problem can be solved by any computer in existence, it can be solved by this minimal set of instructions operating only on natural numbers.
The second conclusion is perhaps even more profound, and it defines the nature of information in the digital age. The fundamental truth of computing is that all data is numerical.
The ability to encode text, images, complex objects, even the source code of our programs as giant natural numbers is the heart of abstraction that makes all digital processing possible.
We now understand the distinction between the theoretical world and the practical world. We use the simple, pure mini-pi model for formal proofs because its provable power guarantees the complexity and user-friendliness of the Python you use every day.
The math provides the guarantee, even if the implementation is, well, a nightmare.
And that guarantee relies entirely on accepting the Church-Turing thesis, that our formal numerical model captures all intuitive, effective computation. We've successfully established the class 4, the set of all functions that are computable.
But here is the final provocative thought. If all this computational power relies on the mathematical properties of natural numbers, and we can mathematically define any function that maps numbers to numbers, this raises a crucial question for you to explore.
Are there functions that are mathematically defined, that we can write down clearly, but for which no algorithm, no computer, and no mini-pi program can ever exist to calculate them?
A compelling question and a perfect place to pause and reflect on the absolute limits of computation. What if the universe contains problems that are mathematically solvable, but computationally impossible? Something to mull over until our next deep dive.